In the previous sections, we focused on interactive systems, such as your desktop or laptop computers, where interactivity is the primary concern because we want the response time for the processes, especially the interactive processes, to be minimal and be able to run many tasks in parallel, concurrently, some of them in the background. Or also the computer systems where the primary concern is CPU utilization, such as in the case of compute servers or mainframe systems. But now we're going to focus on a different type of systems, the real-time systems. And when we talk about real-time systems, then we need to talk about real-time scheduling of the processes in a real-time operating system. So there are basically two types of real-time systems, the soft real-time systems and the hard real-time systems. Soft real-time systems are systems where, different from the regular use of processes, now we're a little bit more concerned about the execution of real-time processes, like, for example, video streaming, where it's important that those processes have more CPU time. More important, their response times is actually much shorter. So it's critical that these processes are getting enough CPU time, but still we don't give a full guarantee. So, but in the scheduling, we pay more attention to getting these processes up and running as soon as possible, so they're more responsive. Whereas in the case of hard real-time systems, this time we really give guarantees. So we guarantee that this process will get into the CPU in this time, and more important, it will complete before its deadline. So there are different uses of such systems, especially for the case of hard real-time systems. For example, in the airplanes, for example, there is still a computer managing the flaps and the rudder and all other components of the plane that are related to aviation. And in such a system, you don't use an operating system like Windows or MacOS or Linux because they don't give guarantees. The important thing is when the pilot decides to move the flaps or the rudder to control the plane, we want to get the response from these equipment in a given time with some guarantees. So it shouldn't be like, well, the system will most probably do it in time, but I cannot not give any guarantees. This is not acceptable in the case of a, for example, airplane, because it could easily end up in a serious accident where lives will be lost. Or in the case of, for example, a nuclear plant control. You would like to ensure that all the safety mechanisms are activated when something is going wrong. And also, before that, you should guarantee that nothing is actually going wrong. So all processes should be completed in the given time. It shouldn't be like one process, very rarely, it's probable that it would be blocking or delaying other processes, resulting in a failure. This is not something that we could tolerate, even if the priority is very low. So you cannot say, with the probability of 1 in a million, this nuclear plant may fail, because if that probability really happens, and if the nuclear plant fails, then it's a huge disaster. That's something that can never be tolerated. Or in the case of, for example, use of rockets or spaceships, you want to guarantee that failure is not an option. So such systems are considered hard real-time systems. Before continuing with the discussion of the latencies here, I would like to discuss several several real-life experiences related to real-time systems. Actually, several disasters related to these. So the foremost example, luckily it was not actually a disaster, it was very close to being a disaster, but the foremost example would be the case of the Apollo 11 flight. So it was, remember, the first manned lunar landing back in 1969. So the mission was accomplished by two vehicles. One was the mothership, which was rotating around the moon, and the other one that really landed to the moon was an aircraft which was carrying only two personnel. So both of these spacecrafts were equipped with 16-bit CPU processors of that time. Remember, this was back in 1969. And the computer systems by then, they had 38 kilobytes of RAM, and the operating system was a priority-based and event-driven operating system. We'll be talking about this slightly, of the size of only 2 kilobytes. So it was quite a simple system, but was doing the task. Now, there was actually a major problem during the landing. When this lunar lander started its operation for landing on the surface, at some point during the flight, they started receiving an alarm. It was the 1202 alarm, and this alarm would repeat itself every 10 seconds. So during the flight, the mission control had a critical point, which was if the lunar lander went below this point, it wouldn't be possible for them to change their minds, forget about landing, and return to the mothership. So there was physically this critical level below which they shouldn't go, and they had started descending. So they should either decide to abort the mission before going below this line, or take the risk and decide to land. And they didn't know what to do by then. And what they did was they turned to the young engineer who had been dealing with and was responsible for taking care of this alarm, and they asked if they should proceed or they should call off the mission, which was politically, of course, another disaster, because there was by then a race on who would land on the moon first, either the Russians or the Americans. So it was this young engineer's decision to give the decision go or no go. And what happened was this young engineer, he says later that by God's feeling, decided for go, and they landed. What happened really was the real problem was the following: the the aircraft had actually two radars. One was the down-looking radar, which was measuring the distance between the spacecraft and the surface of the moon so that it could land properly. And the other radar was the up-looking radar, which was for called the rendezvous radar, because this lunar lander, after the mission on the moon surface was completed, would fire back and go and meet the mothership on the orbit. And while docking to the mothership, it should make sure that it would not crash to the into the mothership. So there was a secondary radar called the rendezvous radar that would measure the distance between these two spacecrafts. And normally, during the landing mission, they were supposed to turn off the rendezvous radar because they were just trying to land on the moon by then, not meet the mothership. So that was not necessary. And what happened was they forgot to turn that off. It was not written in the manual, so they forgot to turn that off. But the task, the process that was supposed to read these measurements was switched off. So the radar was sending the data, but there was no process reading it. So it would just accumulate in the buffer. So that was actually causing that 12:02 alarm. And this young engineer, as I mentioned, had to make a decision in a very short time, and that was a very critical decision. And he luckily concluded that it wouldn't be something very important, and he decided for the continuing of the mission. But as I mentioned, this was completely a guts feeling, and it normally should not have happened at all in the beginning. The mission was successful with the decision of this engineer. Actually, while the operations on the moon stay, which was, if I'm not wrong, around a day, were continuing, they analyzed what the cause of the problem was, and they found out it was actually the switch which was supposed to turn off the radar, and they fixed the problem, and everything was successful. But if the correct decision was not made, it would be a political disaster for the Americans. If they were not that lucky, in that case, there would be a crash on the moon. That would be yet another disaster. So it's important how you do the scheduling, and also how you take care of such problems in a real-time system. Another example is the Tugcu computer, which was actually used for treating tumors, cancer tumors, for radiotherapy. So it was a control system for a radiotherapeutic radiation machine. There was already a system that was running properly, which was the earlier version, Tugcu. But now, in the 1980s, they renewed the machine as Tugcu. And later, they realized that there was something malfunctioning in the system. Once in a while, it caused the death of some people, some patients in US and Canada. At least 6 people were dead because of the malfunctioning of this computer system. And the problem was actually that the operator selected one type of operation in an error, and immediately realized that he had chosen the wrong, he had made the wrong choice. So he would just fix it. He would just from the menu go to the other operation. But since the hardware started acting on what was told in the previous instruction, it wouldn't change the position, and the system was not completely aware of that. And because of this, as I mentioned, 6 patients already died. They later realized that actually even the previous version, Tugcu, also had the same error in the code, because this was a very simple system by then, a DEC PDP-11 computer system, and everything was designed, everything in the operating system was designed by one engineer. And the original Tugcu system also had the same problem, but there were additional hardware sensors and fuses that would detect such errors and not apply the radiation. So these hardware sensors actually acted as an extra safety net against such high radiation. But in Tugcu, these sensors were removed. So in real-time systems, actually, you should therefore have several layers of safety to avoid such errors. Another example of real-time systems would be the Mars Pathfinder system, which was, as you'll remember, famous for the high-resolution pictures it was sending from the Mars surface. But also another famous thing, if you would remember about that spacecraft, was how it landed. It had these bouncing landing procedures. So it just dropped to the surface of the Mars and bounced several times, and finally those balloons would be deflated, and the Mars rover was working over the surface of Mars, taking those beautiful panoramic pictures of Mars. But there was yet another problem, if you would remember that. And the problem was that in the very beginning, the system would randomly just reboot itself. So the Mars rover would reboot, and of course, when it rebooted, the connection between the Mars rover and the control center on Earth was lost. Then, after it rebooted successfully, the connection would be established again. Of course, it was there was too much delay because of the distance between Mars and Earth. But then this would repeat itself. So it took some time to realize what was causing the problem and how they would fix it. Luckily, they had an exact copy, a sister copy of the rover also on Earth. So they created the same conditions and they found out what the problem was. And luckily, again, there was a C interpreter already in the operating system that was still left in the system. So with the help of that C interpreter, they were able to fix the problem, and so the Mars rover was able to function properly, and it has been sending all these beautiful pictures. Now, what happened there was the following. There were several processes that were communicating over an info bus, the information bus. And that information bus, as we will discuss later in synchronization, was protected using what we call mutexes for this shared access to this bus. Now, these processes that were trying to communicate over the info bus had different priorities. Like, for example, there was the meteorological data gathering process, which had low priority. There was the communication process, which had medium priority. And there was the administrator of the infobus administration process, which had high priority. But once in a while, the following problem occurred. The meteorological data gathering process, which had low priority, would try to measure or transmit the meteorological data. Okay, so it would lock the infobus to be able to do this data exchange. But then the infobus administrator, which had high priority, would try to access the infobus to use it. But since it was locked by the meteorological data gathering process, it would get blocked until it was released. Meanwhile, the medium priority process would be activated, the communication process would be activated by an interrupt. So once again, the low priority has locked the bus, the high priority is trying to access it, so it's blocked because of a low priority process, and the medium priority process was activated by the interrupt. So although the low priority was holding the bus, the medium priority was activated because there was an interrupt. And this high priority process would keep on waiting and waiting and waiting for a very long time. And because of this, the watchdog, remember you also have a watchdog in your project, the watchdog will realize that this high priority process has been blocked for a very long time and doesn't know how to handle it. So the best solution, of course, would be reset the whole system so that you get out of this deadlock. That's why the system would once in a while just suddenly reset, because it was the watchdog that detected the high priority process was not able to get what it required, and it was blocked. So this is what we call priority inversion, because the high priority process is blocked due to a low priority process. So this was yet another problem, but as I said, luckily they had a similar system on Earth. They tested and found the cause of the problem, and then they were able to fix the problem using the interpreter. The fourth one was the Ariane 5 rocket, which was shot at 1996, and 40 minutes after it was fired, it disintegrated and crashed, and that was again due to some problem in the real-time operating system due to the gyroscope sensors. So all these are examples of the incorrect use of real-time operating systems or errors in real-time operating systems. So you should really be very careful with these systems, because most of the time the results are ending in disasters. So coming back to our discussion here in CPU scheduling for real-time systems, we have two different kinds of latencies here. One is the interrupt latency. So you have some task running, say task T is running, and an interrupt occurs. So the interrupt, from the point the interrupt occurs till the time the interrupt service routine, the ISR here, starts, that's the time what we call the interrupt latency, which is composed of the interrupt arriving, and then you determine the type of the interrupt, and then you decide to do a context switch to the interrupt service routine for that type of interrupt. So that's our interrupt latency. And in real-time systems, we'd like to keep this interrupt latency as short as possible, because we want to react to the interrupts as soon as possible. And the second one is the dispatch latency, which is the time for the dispatching operation between the current process and the next process. So in the case of real-time systems, when an event occurs, you have to give a response. So the response time is the time from the event occurring till the response to the event, which is composed of, if there's an interrupt, and typically to do the dispatch, you should have the interrupt. The interrupt processing time first, and then you decide to do the dispatch, but there could be conflicts between the interrupts. If there are several interrupts, then there would be a conflict with which interrupt to be executed at the moment. And more important thing is, you need to, if there's the kernel process running, you need to preempt the kernel process which is running in the kernel mode. So you preempt that, and to be able to do that before, you should resolve the conflicts and release the system to low priority process. Release, sorry, the resources held by the low priority process to the high priority process, so that you don't have such, for example, priority inversion problems. So the dispatch latency is the time for the dispatch operation itself, but before the dispatch operation, you should resolve the conflicts. And in real-time operating systems, as we said, you should reduce both the interrupt latency and the dispatch latency as much as possible. So in the following scheduling methods we're going to discuss, that will be our primary concern.